स्टूडेंट्स, स्वागत है आपका डॉक्टर सौरभ से क्लासेस में। और आज हम लोग सॉल्व करें ISI M.Tech PCB का सॉल्यूशंस 2025 का सीरीज़ है और इसमें हम लोग आ चुके हैं क्वेश्चन नंबर 4 में। तो चलिए ये वाला सॉल्व कर लेते हैं। लेट आर बी द दिया गया है, लेट आर बी द। सो हियर विल राइट द it's a balanced binary search tree having m modes where each node contains an integer appointed to its left child and appointed to its right child. Okay, so we know that insertion and deletion of nodes in such a tree can be done. Time is a worst case, so we have to describe the procedure. Previous is that give the root r and any integer z output the node containing the largest integer which is smaller than z. So the worst case time complexity of the procedure should be, and we have to provide a justification for the complexity. Okay, so first we understand the problem. So here it's of with root. Okay, so for any integer find the largest value less than. Okay. So here what is the property? That for each node left child is less than and the right child is greater than. So here now this tree is balanced, so its height is what? It will be correct. So we must take advantage of that for efficiency. So then in Python, how it will look like? So for the Python, function previous, okay, r z and predecessor is 9. So current is r while current is not 9. So if current dot value is less than z, so here current is a candidate. Go right for possibly larger candidate. Okay, so go possibly for larger candidate, then predecessor is current and current will be current. So else go left to find smaller elements. Okay, so current is current left. Okay, so then we return the predecessor. Return the okay. So what is the to understand? I will give you the explanation. So if we go for the explanation of this logic, so if current is less than Z, then we might have found a new predecessor. Okay, so but maybe a larger valid one exists on the right. So we move right. Okay, so now on the other hand, it's if current value, then even if current, so we must go left to find smaller values. So this works down a single path of the choosing right or left at each step. Logarithmic height traversal, you can say. Logarithmic height traversal. Okay. So there is a time complexity justification here. What is that? At each step, we move one level down the tree. Okay. So in a balanced like height is what? Log n. So in the worst case, we make comparisons and pointer moves. So then the total time will be, so here the function previous, it traverses the tree like a binary search. It keeps track of the best predecessor found so far. Okay, and it makes only one decision, left or right, at each level. So there the total comparisons is this. So therefore the algorithm is correct and efficient. Okay. Now there is a second part to this. What is that? We are being asked to design what? Find largest that returns the kth largest element in a balanced binary search tree. Okay, in time while ensuring that insertions and deletions still take. So we augment each node to store. Okay. So size is what? The number of nodes in the subtree rooted at this node, including the node itself. Okay, so here it allows to determine the rank of a node. Okay, its position in the sorted order in constant time and at each level. So let the size node is number of nodes in subtree rooted at node. So then in a binary search tree, the right subtree contains all the greater elements. Correct. And the kth largest element is what? Its size r k plus 1 smallest element. Okay. So we'll write the algorithm here for the Python code. So Python. So function find largest node if node is null. Return null. Okay. And right size is if node right is none, else node right size. If right size is, then return node found the kth largest element. Okay, so right size k return find largest node dot k. Okay, so else return find largest node dot left comma k right size is 1. So here at each node what you see? So at each node if the subtree has exactly elements, that means current node is the kth largest. Okay, and if right has, then what happens? We move right. Okay, and else we move left. But we subtract right size plus 1 from Q. We have skipped those many larger elements. So here maintaining the size during insert or delete. Okay, like during insert or delete, we update size. Then while returning from recursion, and now since BST insert or delete is already in balanced trees, so maintaining the size adds this. Okay, so the time complexity. So here what we understood, that store size, so number of nodes in each subtree at each node, correct? What is the procedure? Recursively compare k with y to decide where to go. And what is the complexity? There is a query and insert or delete with size update.